Hydrostatics, example 2. Here we have a U-shaped tube called a U-tube, partially filled with water. And if we pour oil into the left side, that oil will float in a column on top of the water because oil and water are immiscible, meaning they do not mix with each other. And also because oil is less dense than water. Note that the water itself has gone down by 1.5 meters in the left side and gone up by the same 1.5 meters on the right side because water as a liquid is incompressible. So the total volume of water must be the same before and after. Okay, your goal here is going to be to determine the density of this oil. And you'll pause the video in just a moment to do that. The principle you'll be using is the idea that pressures are equal at all points on a horizontal line in any fluid. So if we draw in the horizontal line there, dividing the two fluids, the strategy will be to set the pressure here at point A, just underneath the column of oil, equal to the pressure over here at point B in the water. So pause the video now, set those pressures equal using hydrostatics equations you know, and see if you can determine the density of the oil. All set? All right, here's how we do it. What we'll say is that the pressure here at point A can be found by taking the pressure of the gas up above, the atmospheric pressure, plus a rho GD term for this 4-meter deep column of water. So that's the atmospheric pressure plus the density of the oil times G times the 4-meter depth of that oil column. That's the pressure at point A. Set that equal to the pressure at point B, which is also the atmospheric pressure above, say there, and plus a rho GD term for this 3-meter deep column of water. So the atmospheric pressure plus the density of water times G times the depth of that 3-meter column of water. So here, pressure atmospheric can be subtracted from both sides. Then little g can be divided off both sides, giving us the density ratio of the two liquids is equal to the reciprocal of the depth ratio of those two columns. So 3/4 is our density ratio. Thus the density of oil is 3/4 of the density of water, which is our 1,000 kilograms per cubic meter, so 750 kilograms per cubic meter. Another way of looking at this is to note that the water here at points A and B must be holding up equal weights of material above them, since the cross-sectional areas are the same here at A and B. So the weight of this much oil plus this entire column of air going up to space must be the same as the weight of this much water here plus the weight of the column of air above it going all the way up to space. These two cross-sections of the water are supporting equal weights above them. So we could also have gotten to the same conclusion by setting the mass of this oil equal to the mass of this water. Okay, example 3. Here we have a set of tubes with outside air pressure in yellow, and then 3 different gases in these tubes at different pressures. So you can see the water level is at different heights due to the different pressures in these sealed tubes. So what are the pressures in gas bulbs A, B, and C? You'll be computing that in a moment using the same strategy, setting the pressures equal at points on horizontal lines in a single fluid. So take the outside atmospheric pressure to be 1 atm and compute the pressures in bulbs A, B, and C. Pause the video, try that now. Got it? All right, here's how we do. Let's see, the lines we'll draw will be first a horizontal line, say here, at a Z value of 5. And we'll say that the pressure here, we'll call it P5, at the top of that column of water must be equal to the pressure over here, since it's the same water. So we know the pressure at this point must be 1 atmosphere, since the pressure at this point is 1 atmosphere, since that's where the water is in contact with the 1 atmosphere gas above it. And so then the pressure at this point must be the pressure in this bulb plus rho GD for this 1 meter deep column of water. So we write the pressure here, 1 atmosphere, is the pressure of gas A in the bulb plus rho GD. So pressure A is the 1 atmosphere minus rho GD for this 1 meter deep column of water. That's this little column right there. We know that that is going to give us 0.1 atmospheres. So our bulb must have 9/10 of an atmosphere in it, lower pressure here than the air outside. Now, this 9/10 atmosphere gas is still pushing down on the water, but this 1 atmosphere gas is pushing down on the water harder. So in the contrast between the outside and inside gases, the outside gas pushes down harder than the inside gas does. Thus, the water level raises up higher on this side than on that side. It's important to remember that these fluids always push on their surrounding containers and they don't pull. So we shouldn't talk about the low pressure here pulling water upwards. That's not really accurate. It's just that it pushes down hard, but not as hard as this gas pushes down there. All right, so what about the bulbs B and C? For them, we'll draw a line, say, here, a horizontal line to note that the pressure at a Z level of 2 equals the pressure at the base of that B column and the pressure at the base of that C column. So these 2 points must have the same pressure, and we recognize then that the gases B and C must have the same pressure, and those pressures are equal to the water pressure over here at point 2. So we'll compute those by saying that the pressure here at point 2 equals the atmospheric pressure at the top of that column, so 1 atm, plus rho GD for this 3 meter deep column of water, also pushing down here on point 2. So the pressure at 2 is the atmospheric pressure plus rho GD for this 3 meter deep column of water, and that's equal to the pressures at points B and C. This gives us 0.3 atms, so we have 1.3 atmospheres higher pressure in these 2 columns than in the outside gas. And we know that the 1.3 atmospheres in these columns is the same pretty much all the way through the column, since pressure in a gas doesn't change much with height, unless you're talking about heights of hundreds of meters. So our overall picture then looks like this, where here I'm showing with these red arrows the net force on the bulbs or columns, that is on the walls of the bulbs or column, the net pressure force due to the difference between the outside pressure and the inside pressure. So in this column on the left, as we go down into the water, the outside air pressure stays at 1 atm, but the pressure in the water increases, going to 1.1, 1.2, 1.3, 1.4 atmospheres. So the net pressure on a bit of wall here is going to be outwards and increasing as we go deeper and deeper. So this column is most likely to explode at the deepest point where the pressure difference is greatest. That is, if the material is not strong enough to support that pressure difference. In this horizontal section of the tube, we have a net pressure, a pressure difference causing a net force upwards on the top part and net force downwards on the top part. So this section would tend to explode in both directions if it's not strong enough. Compared to the vertical column here with gas B inside it, or overpressurized gas at 1.3 atmospheres, that's going to be pushing outwards on the walls of the column harder than the outside air is pushing inwards at just 1 atm. And since these pressures don't change much with height, we have pretty much the same net outward force per unit area on all of the walls of this column, and also on the walls of the bulb here. So this bulb and C, since it's at the same pressure as B, these 2 bulbs and columns are both in danger of exploding outwards due to the high pressure on the inside versus the relatively low pressure outside. The only section in danger of imploding would be bulb A here, where the pressure is less on the inside than on the outside. So the net force due to pressure on the bulbs and walls is going to be inwards here, trying to crush this bulb if the material is not strong enough to support a higher pressure outside than